So, good afternoon, everyone. So, first of all, I'm a strange professor of physics for two reasons. It's because I do less physics than physicists. And for the second reason is that I'm dealing with sustainability science, which is the interface between social science and the physics of the planet, in fact. I'm a co-founder of the Laboratoire Interdisciplinaire des Énergies de Demain, which is it's written in English anyway, you know, it's the same language, by the way. It's interdisciplinary means there that we try to work together between natural sciences and social sciences, because there is a huge gap and misunderstanding between those two important areas. But sustainability cannot be discussed without the social science and the natural science at the same time. That's one of the biggest issues from an epistemological point of view. So today I have many things to tell you because the question of critical materials is a highly dimensional question. I will not focus so much on the social science side, but it will be present, because I have a few messages that maybe you will not get from social science, but you will get from engineering or physics, right? And the topics that I'm going to talk about are technological metabolism. You know, the notion of metabolism has been born in biology in the 19th century, but it's been translated into social science, as you may have seen before. And there is a planetary metabolism to which the human societies pertain also. I will discuss one thing, that we have to discuss those matters at the planetary scale. It doesn't mean that there are no local effects. Of course, locality does matter, but it's important to discuss at the planetary scale for different reasons that I will try to explain. And of course, I will talk about the link between materials, power, and long-term view. Anything that is before 2050 doesn't interest me, like I like to say. So critical materials are a major political topic. I will give 2 points of view, Western-centered, which is the European Union and the United States of America. There has been an acceleration of that matter from a political point of view for two main recent reasons. Is the COVID pandemic that has shut down the supply chains, and then suddenly people realize how important are those supply chains at the planetary level, and we were missing important products in the Western world, in the European Union, coming from Asia mainly, for instance. And a second event that accelerated that matters from a political point of view is the war between Russia and Ukraine, when the Western world and the European Union tried to take sanctions, economical sanctions against Russia for invading Ukraine. And then suddenly politicians realized how complicated it was to make those sanctions beyond fossil fuels. Since then, there are many political acts that try to focus on that matter. I will not explain them. You can read them yourself. I give you just a reference and you go and see it. There is a huge body of public policies around those questions. I will just present you another report that you can read, because you can download it for free from the European Union website. This is a bit old. I think it was in 2017, I think. I don't remember exactly, but it's been renewed several times. It's a critical raw material for strategic technologies and sectors in the EU. It's been done by the GRC, which is the Joint Research Center of the European Union. And so they were looking at what considers the major strategic technologies, which are renewables for electricity, electric mobility, and of course the section of defense and space. And then they list all the technologies that are considered as strategic: batteries, fuel cells, wind turbines, electrical engines, photovoltaics, robotics, drones. Drones, I don't have to explain how important it is from a defense point of view. And 3D printing and ICT. The only thing that is very strange is that they separate ICT from the rest of the technologies, which makes sense. But I can assure you that in 3D printing there is ICT, in drones there is ICT, in robotics there is ICT, in PV there is ICT everywhere, in fact. It's one of the major foundational technology, and it's one of the most fragile, as I will try to explain. So, and then you have on the left side the periodic table of the chemical elements. And the only thing you have to look at is the colors, which is green is okay, yellow is warning, orange is danger, and red, we are in a mess. Basically, that's what it means. And then you look at the proportion of yellow, orange, and red in the technologies considered as strategic for the EU, and you see that we have a problem. All those materials are critical. Many of those materials are critical, and I can disagree with some of it because you will see that it's a complicated discussion also from a scientific and technological point of view. Meanwhile, in the US, you have the same kind of debate. Although the US has an advantage compared to the European Union, it's bigger and it has more mining, a larger mining industry. But you've probably noticed that President Trump wants to annex Canada and Greenland because those two countries are important mining reservoirs, in fact. So you can have a lot of information from materials from the US perspective, from the USGS. It's an official United States agency. From geology, the G there is geology, right? It's the United States Geology Survey, and they produce a lot of data about minerals and materials in general. And of course, they also do a list of critical materials that is renewed every year. For instance, you can go also to the website of the Energy Department of the US government, and then they make those graphs a bit similar to the one in the EU. Everybody's doing that for the moment. The supply risk, so critical material means you have a problem of supply, and we will see what does that mean. And then, of course, the importance to the energy sector because of the decarbonation, the greenhouse gases reduction issue. And you see that even in the US, you have many chemical elements that are considered as highly critical or critical, the yellow and reddish side. So that's basically it. You can read that by yourself. It's not very complicated from a policy point of view, so it's a major issue. And in the academic world, it's been discussed for a while. I will not make the history of all of that discussion that goes back to even to the colonial empires of the European of Europe in the world. But anyway, Professor Gradle from Yale, I think he's retired now, but he's one of the Americans that drew attention to that. He's a chemist and a chemical engineer, in fact. And you will see the fun for the moment is to redraw and color the periodic table with a criticality score that I will discuss briefly. And so again, it's yellow, it's danger, orange, it's more problems, and red is highly critical. And you will see here, you see here in this periodic table that you have silicon there, which is the base of digital technologies. You have germanium, same. And in fact, all those elements are the one building the digital technologies that we are using. So the most critical elements are those used in ICT. And you see the ICT is the foundational base of all the rest of modern technologies. And of course, we can discuss, for instance, green, copper that is in green. For me, it should be in orange and red, and I will show you why. So the question of supply is a complicated question. That's the graph again. From those graphs come from this publication that you can download for free from the PNIS website. So you will find it easily. So the supply risk is you don't get the materials. And there are many reasons why you don't get the materials. Of course, we may think about geological problems, scarcity. You have exploited all the mine, all the possible mines, but that's only one dimension. That you have technological reasons. It's more and more difficult to use those materials, economic reasons. You have social and regulatory. Some of the elements are considered as bad, and so they are banned from. Of course, you have geopolitical, because of course the mines are not located in one country; they are located all over the continents. And of course, you have the question of what is vulnerability, the importance for the economy or for industrial sectors. So there is a huge discussion about that, identifying what is critical or not. From my point of view, everything is becoming critical, so it's not a big deal to understand that. And then, of course, if you wish, and if you are interested in ecological, environmental issues, there are still environmental issues, right? But the main message is, even if you don't care about the environment and ecological issue, you still have the problem, right? So that's important for discussing for people that are not receptive from a political point of view of ecological disaster. Never talk about ecological disaster. Most of the time I just explain that it's doomed. I will show you why briefly. Of course, if you are burning fossil fuels, you see they disappear. And you know that fossil fuels are a stock, a geological stock. But when you are using copper for wires to transmit electricity, the copper doesn't disappear, right? It's still there. So we could recycle it and then reuse that copper. And then a while ago, again, Gradle colored periodic table. And of course, again, is the reddish is the recycling intensity. It's below 1%. Orange 1 to 10% of recycling, yellow 10 to 25, blue 25 to 50, and above dark gray, it's above 50%. And basically, the weakest zone for recycling is that one, the zone of the digital technologies, okay, except lead and tin, which are classical metals. What we recycle very well are the classical metals. Of course, you see there copper, nickel, silver, gold, platinum, cobalt, iron, manganese, chrome, and so on. Those are the easy metallic elements that are easy to recycle because they are also used massively. If you take a wire, an electrical wire, it's 99% copper. So it's more interesting to recycle an electrical wire than to mine copper, because copper in a mine, in an ore, it's about a few percent, 5% around for the moment. So it costs a lot to extract those 5% and to make a 99.9% pure copper. But from a wire, you start from 99%. So and still you see that copper is not so much recycled. And we can discuss that. I can give you a hint of why. The difference between recycling copper and mining copper is that you can go to the mine whenever you want. Okay? Getting copper to recycle it depends if it's at the end of life of the object containing the copper. So it's not when you want, it's at the end of life of the object, the technological object containing copper. And the second thing you know is to bring back the copper to the industry, the recycling industry. And all that is more complicated than just mining copper. Okay, that's why the main source of copper today is the mining industry and not the recycling industry. There is an important factor is that the wheel of use of a metal, metallic element. In fact, you will see that every industrial process is losing part of the material, right? So for instance, here for nickel, we only recycle 52% and the rest is lost. It's spread out in the environment, including the industry. So, so it's very important to to understand that there is some kind of depletion of those metallic elements, in fact, for the reasons that I just explained. And so what is the question? So the question I'm addressing is the sustainability of the technologies that we use in the Western world that are more or less dominant around the globe for today. The second thing I'm discussing, of course, I cannot do prediction. That I explain because I'm also teaching the physics of the climate. What I explain to physicists is that the temperature that are before today are physics. That's physics. We discuss among physicists, and we have climate models, and we understand the physics of it. But the projection of the temperature for the future, that's not physics anymore, because you have those guys that are called humans that interfere with the physics, and we have model to predict how the physics of the globe works, but we don't have model to predict how human societies work. And so you have to build a scenario, okay? And those scenarios are not prediction. They are foresight guesses, educated guesses, of course. And of course, they are debatable. So if you see the IPCC future temperature, they are based on different scenarios. And here it's the same. So my scenario is business as usual. So I want to keep the present world as it is, as long as I can. Of course, there are industrial innovation, there is new invention and so on. We can discuss that later, maybe. But still, I want to make it last as long as possible. And then I ask the question of sustainability. You know that we do a difference between durable and sustainable. Sustainable is something that is admissible for good reasons and that can be supported. And durable is that it can last long. But if you have Prometheus, that he gave the fire to humans, and he was condemned by Zeus to have the liver eaten every day by an eagle for eternity. That's durable. I'm not sure it's sustainable. So that's a big difference. Then I discuss weak and strong sustainability with a different definition from the people in economics. That's the pleasure of engineers and physicists to change the definitions, or the way around, the economists changing the definitions. So it's based on the time. For me, weak sustainability is something that can last through the 21st century. And strong sustainability is something that will last beyond the 22nd century. And I can ask the question, can we design technologies that are sustainable for centuries or for millennia? And usually, if you tell that to an engineer, he said, you're completely fooled or crazy, it's impossible to do. But it is possible to do because we have technologies that are 3 billion years old. One technology that is 3 billion years old is the conversion of sun radiation into chemical molecules. That's called photosynthesis. It's the same basic physical chemistry for the last 3 billion years. I think it's sustainable. Okay? And by the way, humans are fully dependent on photosynthesis. So the other point is that modern technology are planetary. They are planetary for two main reasons. The first reason is geological. You have to find all the chemical elements and the metals and the metalloids that you use in a technology, and they are spread out on the 5 continents. Of course, there is more copper in South America, for instance, but not only. But there is a geography, a planetary geography of mining that you can have a look at it. And the second reason is globalization, economical globalization. The industry is spread out the planet, especially the digital one, and I will show you that. So the question is, we are designing an energy transition, and until when can I build a wind turbine and photovoltaics, for instance? Is it for 2 centuries, 5 centuries, or a few decades? Okay, that's the question. So the main question is, the central question of the ecological transition, according to me, is the technological systems. Why? Because you see the technological systems are the ones that are sustaining human lives for the moment and improving human lives, because we are about 8 billion humans now on the earth, and it's thanks to those technologies. But the paradox is that having those technologies are also creating problems, ecological problems. It's the notion of Anthropocene that is being discussed. So thanks to those technologies, certain human societies are transforming the composition of the atmosphere, of the continent, and of the ocean. And the result of that is it's reducing the habitability for the earth, for human societies. That's why it's a central question. But you will see that I have a special definition of what a technical system is. And of course, whenever you are using a technology, you need some materials, right? The mic is made of some materials that you have to find. So the most fundamental question is also the kind of materials you are using. And if I have to produce those materials, the next question is the power I need. Our power, you know, it's joules per second. I don't know where you are in physics, but that's elementary physics. So joules measure the quantity of energy, and what measure the power, and the power is the flux of energy. And what makes the T, it's not the energy, it's the flux of energy. Okay? It's a very important difference. And that's why we are in love with fossil fuels, because they give us a kind of, it's a source of nearly infinite power, and I will try to explain that. And I will show you that we don't have a problem of energy. We have so much energy that we don't know what to do with it. The problem is to capture it, and to capture it with a given power. You have to think at the spatial scale. So you have to work at the planetary scale. That's the idea of the boundaries of the Earth, right? We're reaching those boundaries or crossing those boundaries because we are at the end of going west. For if you're remember the Western, they're going west, the frontier, like Americans say. And then if you were looking the old series like Star Trek, space, the final frontier. So it's in the mind of the Western world conquering the planet. It's done. Okay, we are at the border of the planet, and we are crossing the border of the planet. And then, of course, you have to think about the temporal scale. So if you discuss before 2050, then you will say, well, there are some issues, but that's okay. You know, it's like in the French film when you jump out of the Eiffel Tower, and during the fall you say, I'm fine. Until here, I'm fine. And then suddenly there is an impact at the end. So we have to dare to go beyond 2050 and the next centuries. From a physical point of view, that's strange, and engineers don't like that, economists don't like that. Nobody likes that. They don't, because there are too many uncertainties. The only people who like that are the climatologists. They don't show, if you look at the IPCC report, they don't show timescales below the century. It goes up to 2100, right? Because in the last report, what they show is from Julius Caesar to Emmanuel Macron, 2,000 years, right? Because if you look at 2,000 years, then you see that there is something big happening in terms of global warming. And then they can draw graphs for the last 65 million years. And then they can draw a graph for the last billion years. And then they can think what was the climate at the beginning of the existence of the Earth, right? And so, but that's one of the things that we can do because of its physics. But for the technologies and the materials, there is some kind of physics, underlying physical processes that that allows us to build scenarios about that. So what is a technical system? The technical system, to put it simple, is the whole society, in fact. Okay? There is an interdependence between materials and the energy sources. Depending on the kind of sources you have, you cannot do some materials. Why is the Bronze Age before the Iron Age? Nobody knows. It's because fusion temperature of copper is below the one of iron, so around 1,000 degrees, let's say. But then if you want to make steel and iron, then you need to reach 1,500, 1,600 degrees Celsius, right? For that, you have to master technically what an oven is at that temperature. And the oven shouldn't melt because it contains iron infusion, right? Then, of course, you can see the evolution from the beginning of the Neolithic up to the 18th century. I choose Paris as an example. You know, Paris is the center of the universe. And so, so you have the iconic Notre Dame. What is it made of? It's made of minerals, mainly stones. There is a huge forest of 800 oak trees that burned recently, that's been rebuilt. Then you have a few tons of metals for the structure and for the glass, and you have the glass for the windows, right? And then the rest of the society is based on the workforce of human animals. It's biosource products, and the mechanical sources are the wind and the water, but to produce mechanical forces. And that is the basic thing we have until the 18th century. At the end of the 18th century, in the UK, they transformed mine coal into something that is called coke, because they were using that to make beer, which is an important issue. But then they realized that with that you can do much more than beer. You can build a big oven and produce steel as much as you want. So you can build the Eiffel Tower, which is about thousands of tons of steel. It's not exactly steel, but it's similar. Why? Because you have a coupling that you have between the mine coal and at the same place the steel industry. And then you have the steam engine. That's the start what some call the Industrial Revolution. And we are still the children of that. We are not children of the Enlightenment from a technological point of view. We are the children of the 19th revolution. And then at the 20th century, you have the Arche de la Défense, which is huge. And you see the size of the humans there, but you know those buildings, I suppose. And what do you add? You add oil. That's an oil well. Do you know where it is? It's near Bordeaux. There is some oil in France. Well, it's not in use anymore because of regulations. Then you add electricity and, of course, nuclear power plants. And oil is used as a fuel, but it's also used for chemical reasons. It's one of the raw materials for the petrochemistry, which makes all the polymers, the plastics, right? And so if you look at this building, it's mainly concrete, glass, and polymers. And of course, you can only use that kind of building if you have electricity. You switch off electricity, you don't have air conditioning, and you have to walk the stairs for a few hours to reach the last floor. So a technological system, I use the anthropological point of view, right? Not the engineering point of view, not the physicist point of view. The physicists and the engineers say, oh, wait, yeah, technology, it's some technicalities. How do you make a plane fly? How do you make a boat float and things like that? Then I need some materials to build the plane, and then I need a source of energy, and that's it. That's the technical solution. That's not true. In fact, you need the politics behind using planes. You need the geopolitics of planes. You need a socio-economical system that allows the plane to fly. And you have norms and social practices that are changing, that are producing the technology, but that are changed by the technology. And of course, you need the know-how. You need to transmit the know-how by teaching. That's what we are doing now. You need the research to produce new materials, new technologies. But also, you need the humanities, the kind of imagination you use in the culture. One example is what is the imaginary of Elon Musk? Old science fiction from the 50s. That's mainly what his imagination is. And old stuff from the 50s and 60s, before we were discussing what we are discussing today. And then cosmology is not what the physicists do, is the philosophy of nature that you are in. And it's different human culture have different perception of how the world works, and I'm giving you a point of view from natural science. But you see the big issue. To make a technological system work, you need all that at the same time. It's a system, right? And you see the big problem is those guys here that are studying that are the social scientists. And the guys up there are the physicists and engineers, or the chemical engineering, all those guys. They don't talk to each other, right? And engineers don't know anything about what's happening below. And some people here are lost in politics, but they tend to forget about the technicality of the issue. One example, for the last 40 years, we are discussing about circular economy. It's not there. Then you may list the reasons why it's not there. It doesn't exist. You have political reasons and so on and so, and you can write thousands of books about the political reasons why we don't have circular economy, but there is one point that it's not a technical problem that has been solved. We don't have technical solution to make the circular economy. So the research has not been done. And the people who are discussing, because I'm in a project, in a national project about recycling, so the scientists that are discussing recycling are not aware at all of those issues, in fact. And that's one of the main difficulties of sustainability science, is that there is a huge gap between social science and technical and scientific and technical sciences, right? And it's a system. I haven't shown it that, but it's interacting. What is a system? The system is a thermostat that makes this room temperature. You need several things. You need a thermometer that measures the temperature of the room. You need a heater that you can switch on and off to heat the room, okay? And then you need some device that compares the temperature room with the desired room. And if you put those three systems together, you can hope to stabilize the temperature in the room. If you remove the thermometer, it doesn't work anymore, right? You need the three at the same time working together, okay? If you remove the heater, of course, it doesn't work. If you remove the comparison between the desired temperature and the actual temperature, it doesn't work. So a system is a set of elements that only works if they are interacting with each other. And what I'm saying, that's the equivalent of a thermostat. They have to work all together all the time to make a plane fly, right? And you can easily, from political reasons, decide no planes is flying anymore. You've seen Dune, the film? What is forbidden in Dune? From a political point of view? No, the artificial intelligent machine are forbidden because there was a big war between humans and intelligent machine that humans at the end of the day won, but then they realized that it's too dangerous, so it's forbidden. It's in the film. If you haven't read the novel, you can look at the film, the movie, there is a sentence like that. Intelligent machines are forbidden. So politics, so you see that it's not because you can do AI that you have to do AI. You can just forbid to do AI because you estimate that it's not good. So the second point, which is very interesting, is the Earth System Science. That's a report from NASA that is being destroyed for the moment in the US, the scientific program. That's a report of NASA to the Academy of Science of the United States. And the most important thing is this graph here. So you have all the physics of the planet, the atmosphere, the ocean, water, marine biology, terrestrial ecosystem, the sun, the volcanoes, whatever, the tropospheric chemistry, and then you have this little square there, which is human societies. And why is it important? Because this has become a major change in the physics of the planet, okay? So how do we, and so if you want to understand what we can do from a sustainability point of view, you have to understand how the Earth works, in fact. And we have some understanding of that thanks to the natural sciences. So the other, but that I've told you before, the other concept I use is the notion of metabolism. So there you know that you have a metabolism, especially people doing sports. They're trying to hack their metabolism all the time. There you don't know you have a metabolism, or you may know you have if you have had lessons in technological metabolism, industrial metabolism. You know the first one who was talking about industrial metabolism. It's Karl Marx in the 19th century, because he read the book written by von Liebig, the chemistry guy, who was discussing the metabolism of plants and animals in a farming context. And then Marx read that book and said, oh, metabolism of the agriculture through plants and animals. But in fact, in a factory, it's the same kind of things. You have a flow of materials entering, a flow of materials getting out, and in between, you have some physical chemistry processes and source of energy to make it work. So you have a metabolism of the iPhone. That's an iPhone, by the way. And you have a metabolism of the whole Earth. And in fact, those sections, those divisions are artificial. In fact, there is only one metabolism, which is the one of the Earth. We divide it in two pieces to understand it, right? But you may say, yeah, but do the organisms need the rest of the planet? Of course they need the rest of the planet. The first thing they need is the electromagnetic field produced by the core of the planet. If you don't have that, you're burned by the sun, by the particles emitted by the sun. You need the gravitation, okay? You need volcanoes. Why do you need volcanoes? You need volcanoes to re-inject carbon dioxide in the atmosphere. Imagine you're producing animals in the oceans, or plants, and they are using carbon. At the end of the day, they die. They sink to the bottom of the ocean. What do they become? Fossils or rocks. So there is a sink of carbon in the crust of the Earth. So at the end of the day, when all the animals have used the carbon available in the atmosphere, or the plants, then it becomes a rock, and that's it. That's the end. It may take a few billion years, or it may be rapid, but if you don't recycle the carbon out of the rocks, you're doomed to disappear. And what is recycling out of the rocks the carbon? Volcanoes, okay? Because it's melting rocks and injecting tons of carbon dioxide in the atmosphere. And that's why I'm here talking, by the way. Without the volcanoes, the fate of the Earth would have been completely iced after the invention of photosynthesis. So the next question is, okay, I want to build materials, but I need energy. Oh, we have a problem of energy. Saying we have a problem of energy is like, it's partly in French. I don't know, it's French because that's the name of the boat, by the way. So there is a guy who decided to prove that you can survive in the ocean, where in the middle of the ocean, you have a problem if you want to drink water, which is strange because you're in the middle of the water. So you don't have a problem of water, you have a problem of salinity of the water. And that guy wanted to prove that if you drink some rain plus some salty water, you can survive for a few days, a few months, okay? It's exactly the same with the energy. We don't have a problem of energy because we receive a lot of energy from the sun. We have a problem of catching that energy, the way you have the problem in the ocean to catch the water without the salt, right? So the use of energy for the whole human societies for 1 year, it's about 600 exajoules. That's 50 minutes of sunshine. So every 50 minutes, we receive the whole consumption of energy for all human societies for a year. So it's raining energy, okay? We are in the flux of a constant flux of energy. So the quantity of energy is not an issue, but the power of energy, the flux, is important. Because in fact, if you look at what is called the solar irradiance, it's about 1,300 watt per square meter. And then it's per square meter. Why is it per square meter? That's the physics. It's like that. And that value depends on what? The nature of the star, the size of the Earth, and the distance between the Earth and the star, the sun. You cannot change that, right? Yes? Yeah. The whole Earth. Then you can start play with the numbers. If I remove the ocean, if I only a portion of the continents and so on, but still it's a lot. Okay, it's still more than we use for the moment. And so the problem is that that number you cannot change. It's part of the astrophysics of the system, and it's 1,000 watts per square meter. But 1,000 watts is nothing. You have about between 5,000 to 10,000 watts that you use in your apartment. Okay, so we are constrained by the power. We're not constrained by the quantity of energy. Then fossil fuels. That's my favorite graph. Fossil fuels are a parenthesis in the history of the humans. Okay, so I've done a graph between 15,000 to 25,000. The red line, it's not a prediction, by the way. So don't panic, but you still could panic about that. So if you look at the red line, it's the total consumption of fossil fuel, gas, coal, and oil. It's a stock. In fact, we are using the forest that existed at the Carbonifere and Devonian time, a few 100 million years ago. In fact, we are using the sun there. Fossil fuels are the sun of a few hundred million years ago, in fact, that were buried and transformed by the geology. So at the end of the day, there will be an end of that. Nobody knows exactly when, but at the rate at which we are using it, it could be during the next century. And so you see, that's a small window because Homo sapiens is 300,000 years. Neolithic, it's about 15,000 years. Okay, you have many, many empires and kind of societies that existed. This is just about four centuries, and 2 are gone already. Okay, that's a window, a small window in the history of humans. So we've been living without fossil fuels for 1,000 years. And if you go to Italy and if you look at Herculaneum or Pompeii, if you look at those cities, they were expanded, in fact. So it's possible. So why do we use so much fossil fuels? That's one of the questions. Why? But why? Why? It's because we want to produce that. So yeah, that's a nerdy graph. Sorry, there's a physicist talking here. So it's a log scale. There it's a log scale, and there it's a log scale. These are the energy sources. These are the materials you see there: copper, germanium, gold, iron, lead, blah, 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 all the list. Each time you see a straight line, it means it's an exponential. An exponential in log scale is a straight line. So you see this one, which is probably iron. It's an exponential, and you have the line of the copper there in orange. It's exponential since we have data about it. Since the beginning of the 20th century, the production of most of the elements, of the metals, are exponentially growing. And when I say it's exponential, it's mathematically exponential, right? It's not a metaphor. I can make a curve fitting and with an exponential, and it fits 99.99%. Okay? There is an end to that also. Because the amount of copper or iron or lead or whatever metal in the crust is also finite. The only difference between the two is that when you burn the coal and so on, it's gone. But when you use the iron, the copper, and the metal, it's still there. And you may hope to reuse them. But in fact, if you remember the graph I show you with the steam engine, the train, the steam engine, then the steel factory and the coal mine, it's a system. It's the same thing as the thermostat. Because you have coal, you can build a steam machine. Because you have a steam machine, you can extract more coal. Okay? And so there is a positive feedback loop, a snowball effect. More coal, more metals, more coal. And there is a call for coal, because you want to use metals. Because human societies have been using metals since a long time, thousands of years. And you know why it is so important, metals. What's the first usage of the metals is, of course, arms to make wars, right? So it's again a system. That's why there are those brackets. It's not energy on one side, source of energy on one side, and materials on the other side. It's together like the thermostat. So if you suppress the fossil fuels, you don't have the same quantities or even the same kind of materials, because you have to find the power from somewhere. And I show you the hint. The hint is that if you get it from the sun, you need more square meter, which is an issue. And if you get it from coal, you just need to mine the coal mine faster. And that's a technical problem. And engineers are smart guys. They solve the problem. So if you want to extract oil, gas, and coal fast from something, well, it's been done. It's been solved technically. Okay? So it's very important. I know I always think it's quite trivial what I'm explaining, but you have people still today, the engineers of EDF that have produced electricity, they're discussing energy. And for them, there is no problem. It's changing, slowly changing. There's no problem of materials. I want to increase my electric grid by 25% in the next decades. Where do you find the copper? It's not an issue. I just want 25% more electricity grid, okay? And then, of course, here you have people inventing materials. Oh, I want to produce, by the way, you know, the quantity of copper we are producing is 24 million tons of copper per year. Per year. The iron we are producing is 1 billion of tons of iron per year, because we are using it. So those people are discussing, oh, I want more materials, but they don't think about the energy because it's available for the moment. And then you have, this is textbook science. That's one of the textbooks I use for the physics of materials. So you see there is a graph here, that's the time scale, right? At the end of the 18th century, there is a switch between biosource materials to mineral source, which is totally unsustainable, non-renewable materials. But the good thing is that we've been inventing many kinds of different materials, metals, polymers, ceramics, glasses, hybrids, and so on. It's booming, but at the same time, you have the quantity that have been booming, right? Thanks to what? Thanks to the use of fossil fuels since the beginning of the 19th century. And at the end of the day, what we are doing is producing more materials than the biomass of the planet. That's one thing that is amazing. The quantity of materials that we are producing for infrastructure is bigger than the biggest biomass of the planet, which are the plants. So the plants, the trees, shrubs, and so on, are about 900 gigatons of materials. And the buildings and infrastructure is more than that, is 1,100 gigatons of that. We produce more plastic, twice as more plastic as animals on the planet. So all those materials end up on the planet, right? It's not completely sent to space, which means they are still there, transforming the ocean, the crust, and the atmosphere. And you look at it, that's a bit old, but if you look at the quantities, it's in millions or billions of tons of all kinds of materials. So is there an end to fossil fuels if we still use them, if we keep using them? You know, that's the if, because they are humans. It's not a physical process. It's human societies that are using it. If human societies or some human societies decide to use it until the end, when is the end? That's the question. There is an end. The question is when. If it's in the year 3000 something, I wouldn't be talking about it, right? If it's before, I would be talking about it. And it's before. Well, the educated guess it's before. So that's for oil, the peak oil debate, which is still going on. You see there are two phases for oil. You have the phase of crude oil, which is exponential from the beginning of the 20th century up to the 70s. Then suddenly there is an issue here, and then it starts in a linear way. And then we want to extrapolate the curves, and that's one of the assessment of how much oil. By the way, you see that here you have two colors of curve, and there you have a zoo of color. Why? Because in fact, we are looking for any kind of thing that looks like oil, because there is some panic in the room. So the good crude oil is finishing, and we are using many other kind of oil that are different chemical composition to supply still the demand of oil, right? But you look at the time scale, this is the end of the century. So after 2050, it's going to be an issue. Again, it's not a prediction. It's an educated guess. So it's not a prediction, but it's not n'importe quoi also, right? It's not completely stupid. It's educated guess. But then you say, well, but you may find, I suppose you don't care about global warming. And so we say we just have to find more oil, and that's it. Problem solved. Well, there is still Greenland, there is still North Pole is melting. So there are places to look for more oil. But in fact, the oil companies are finding less oil. They're looking for, it's more and more expensive to look for oil, and they find less and less new sources. So that's a big issue, because if that's the end of the beginning of the end, it's not the end, the beginning of the end of oil, you have the problem of the materials. How are you going to do all those materials? The second point is when the drama is starting. The drama is not starting at the end of oil, of course. The drama is starting when it starts to decline. Why? Because there is not enough for everybody, or there is not enough to cover the demand. And so the demand has to adapt to the production. For the moment, it's more or less the production adapting to the demand, right? So the demand has to adapt to the production at the global scale, but also in the regional scale. So what's so interesting in Venezuela for the Americans? Besides, of course, democracy, because blah, blah, blah. What's so interesting in Venezuela? Oil. Oil, of course. Of course. Of course. So the end of fossil fuels, what are the reasons? You have physical causes. That's physics, right? The depletion, like I discussed, geological resources. It's technically increasingly complex. Some type of oils are complex to extract. They cost more. They are more difficult to extract. Then, of course, it increased the energy power requirement to extract them. And then you have systemic impacts. There is a regulation of human societies that has been switched on, which is climate change. Climate change is a feedback that is regulating what the industry can do and what. And I'm not talking about rational discussion. It's being your industry is completely flood or burn, and that's it. Okay. But if there are also anthropogenic causes, so we have a brain, and with the brain we take rational greenhouse gases emission reduction for environmental reasons. With that brain we can also invent new forms of sufficiency, or we can invent a new industrial metabolism that is not so difficult to find because it was there before. And we have much more knowledge from a scientific and technological point of view than before, if we keep the knowledge. So there is an issue. The end of oil is not that far away. The end of coal and gas is a bit further, but still it's an issue, because if you remove it, remember the system, if you remove it, you cannot have all those materials. What about copper? That's one of the graphs that was surprising me when it was published in 2014. So the people were, the author were discussing what the miners have in the mine. Okay, so there are copper mine, and in Chile, in Peru, so most South America is a big producer, Mexico, and the rest of the world, and US, Australia, and so on. And so they make an educated guess of how much copper can we extract for all known mines, and they said the peak is at 2040. From an industrial point of view, 2040, it's tomorrow. So this has been a bit worrying, a bit striking. So I've redone the curve. And for the last 12 years, I'm redoing the curve. And each time I catch a student, he redoes the curve. And that's the curve I've done. So the blue dots are the data from the USGS. By the way, the day Trump decided to erase the data is gone. No? And I'm not sure any other country has as much data as the USGS. And so the blue dots are following a curve, and then the prediction of the peak is 2029. So I was too scared to show that. So the people are going to think I'm completely stupid or crazy or doomsday guy obsessed by the end of the world. So I said, oh no, it's okay, it's 2080, the resource one. So what's the difference between the two curves? That's what the miners say they have in their mind. I'm not saying it's correct, that's what they say there is. And that's why the geologists say we can find. Okay? But then the resources have to be transformed into reserve by increasing the mining industry. So if you want to transform the resource into reserves, you have to open new mines. So it's still an industrial process that takes time. But anyway, I was saying, well, yeah, with copper, it's all green in all those criticality assessment. But still, 2080, for me, it's highly critical because no copper, no electricity, no chocolate. It's a bit annoying. No Instagram, no picture of cats. Imagine that, it's impossible to imagine. So it's a big issue. No water, no food, and chaos within a week in a Western country, in a Western city. You've cut the electricity of Paris, it's a war zone the next week. So, and then suddenly there was the International Energy Agency, which are not ecological punks, right? Those guys. And then they have produced, every year they produce a report. And then in that report, in 2024, they made a forecast of the copper mining production. That's the red dots. I don't know. So it fits with the prediction there of the other red line, but it's more pessimistic than the line. So, so it's a big issue, and copper is a critical material, and without copper, no electricity and so on. So I'm waiting for 2030 because I want to see if the blue dots are going to follow the curve or not. I'm waiting for the last 14 years for that moment. But of course, it's a big issue because it's one of the major infrastructure elements for electricity. Then you can do that. I've been doing that for many kind. You have silver here. What do you do with silver? Photovoltaic panel, for instance. Not just jewels. It's a good electricity conductor also with gold. But you see, we are reaching the peak of silver, and there the blue dots are falling back. But okay, you can you steal all the cutlery in silver to reuse it if you want, but still. Then you look at the other metals. You see there you have steel, you have lead, you have aluminium, you have which one is that? Tin and zinc. Okay. And in fact, if you do that with many elements, many of the metals, you find this foresight that all the peak dates fall into the second half of the 21st century. So, same as fossil fuels. Okay, same reasons. Either the geology and the technology will stop you, or being clever will stop us. So hitting the wall. Then the chemists understood that. They redraw the periodic table. The size of the square is the availability on the planet, and the color is again bad, very bad, extremely bad. And again, the red side is this one, and the little square is a smartphone. It's the elements used by a smartphone. basically the most endangered species are the digital technologies, right? From a material point of view. Okay, you see there is a big issue, and it's a huge fundamental question, in fact, for Western societies. But that's not the end of it. Who is selling mining products to the European Union? That's again, it's one of the reports from the GRC. That's what I say, you need a planet to build technologies because you need to buy from all those countries. And it's not all the elements, but the elements that are considered as strategic. And you see that Russia, for instance, is an important supplier of mining products to the European Union, which is a bit annoying when you want to take economical sanctions. So it works more or less for oil, gas, and stuff like that. But then what about the mining industry? And then you see, of course, that there are not so much, there are production still in the European Union, but less. Why? Because we started 3,000 years ago, or 2,000 years ago. You've empty coal mines in Spain. You have a famous empty coal mine in Spain that has been emptied by the Roman Empire. Okay? And so when Spain started to colonize South America, they found plenty of gold, El Dorado, okay? And they were so happy because the gold mines were empty in Spain. And so you see that you need the planet from a geological point of view. It's the same from the US, but different. I mean, nobody is completely autonomous. But the autonomy depends on the size of the crust that you have. You see, Russia has a big chunk of the crust, China also, and the United States also, and Brazil also, for instance. Okay? Then if you look at the industry for ICT, how do you do a computer chip? Those are the companies that are also spread across the planet thanks to globalization. And so because what's the answer? That's a political discussion we are having in terms of geopolitics. What was the answer of Europe to resources? It was imperialism. Okay, the British Empire was also using the resources from the empire. Same for the Spanish one before, same from the French one, and so on. So colonization was a way to address this issue of grasping the resources. But imperialism from a geopolitical point of view is coming back. If you listen to what the US is saying, if you listen of what the others are saying, it's a new form of imperialism. But imperialism doesn't work well with the classical globalization, because either you're friend or foe. Okay, but still the globalization of the 90s and the beginning of the 2000s was spreading, the Western world was spreading its industry mainly in Asia, but across the planet. So we've been addressing one question from a geopolitical point of view it's one of recent papers we've published, it's open access if you want. It's what is doing China? What China is doing for the last 25 years? Well, they've been spending billions of US dollars investing in whenever you find a mine. Okay? And so they have, you see there, the domination, the red bar gives you the domination of China in the production of the elements. And you see some elements are nearly 100%, the rest of the world is 100% depending on China. And of course you have geopolitics. For instance, from 2005 to 2013, they were investing a lot in Australia, because Australia is also a very big mining country. But then suddenly the US was upset by the presence of China in Australia, and so China switched to South America. And you see that they are investing billions of US dollars in Peru, in the energy sector, in the metals and sector, the mining sector, and of course transport. And you see that the amount of the investment of the red line, the investment of China in metals is about 200 billion US dollars So that means that 25 years ago, the Chinese government understood that. And they started a geopolitical policy of vertical integration from the mine up to the final product. So they don't want to sell copper anymore to us. They want to sell us electric cars. Okay, that's the big issue. What was the European doing during that time? I think they were sleeping. But at the same time, when you see the investment in South America, remember South America is the garden of the United States. If I don't know if you have a little glimpse of the... And then they don't want anybody else than them in South America. But then suddenly China has a foot on South America. And what were doing what were the Americans doing from that time? Probably sleeping. But they've waken up and they've elected Trump. Which I don't know if it's a good thing, but we'll see. So basically, the issue is the following. Our industries, when I say our industries, the Western industries, is from the mine to the trash. It's a linear process. When you extract products, mineral products, you build purity, which goes against the second principle of thermodynamics. You disperse all the elements into stuff, and that stuff finish up as a waste. So that means that, for instance, digital technologies have built in a process to create scarcity. The digital industry, the digital technologies industry, is creating the scarcity that will end up the digital technologies. And so, for instance, why? Because you have, I don't know if you've seen there. Again, you can. It's public, so you can see it. The Global E-Waste Monitor. It's a United Nations program. And you see, we are in 2022. We were producing 62 billion kilograms of e-waste. Do you know where it ended up? Well, nobody knows exactly. In fact, somewhere on the planet. And they say only 22% of this e-waste was documented as formally collected and recycled. It's not true, it's not recycled, but that's another discussion, what recycle means. For me, recycling means you have some kind of atoms in this table. If I want to recycle this table, I have to get back all the atoms and redo the same kind of table. If not, you have to get the atoms from somewhere else. And we are not getting any kind, we are very far from getting all the elements from the e-waste products. But still, you see why it's so critical, why the materials for digital technologies are so critical. Of course, there are rational solutions that I was discussing, but still we need probably more time that people realize that, politicians realize that. So we are in a trap. We are in a trap. A paradox in terms of materials is that in terms of material you have to do less. To do less, why? To avoid accelerating the scarcity, the depletion, and if you want to address the climate change issue, it's also good to reduce the greenhouse gases emission. But if you want to reduce the greenhouse gases emission, you have to electrify your industry, and then you need more. So, for instance, the Western world wants to do less and more at the same time. You know, when you have to do less and more at the same time, what is the final answer? You do more. What else? Okay. So I have a PhD on an engineer that is discussing, okay, we want photovoltaics because it's a way to reducing the greenhouse gases. I know I have to talk about charcoal and coal at the end, but I will go fast in here. And you see, can we have the net zero emission scenario of the International Agency during the 21st century? The answer is it's going to be complicated. At the second half of the after 2050, the photovoltaic industry will need more than 50% of all copper production. It's not gonna happen. Okay, because I'm very long, so we have to install a recycling industry as fast as we can. So I just want to discuss, just for fun, that I like that. So that's the kind of machine you need to buy to build a computer chip. That it looks like that, the factory. It's also made of materials. And then I realized I was looking at the industry, and then I realized that those guys, Air Liquide, which is a famous French company, DuPont and Dow Chemistry, they were chemical companies. Air Liquide is producing gases, like the name says it, Air Liquide. Air liquid. It's the same in English, in fact. And then I was wondering, oh yeah, by the way, that's true. To build a computer or a chip for a computer or whatever, digital technologies, you need gases. How many do we know? How many gases do we need? Then I started to try to make the list. Here it is. It's not exhaustive, it's what I found, okay? Here it is. That's the list of gases you need to build a computer chip. So okay, so I will conclude on that. What's the problem with, what's the problem? Let's go back to the center of the world in Paris. So can you do the Eiffel Tower in the 18th century? You know, in the 18th century, there is a famous guy, which is Buffon, doing natural science, but he was also fond of metallurgy. So he had a forge in Bourgogne. You can visit it, it's nice. And he was producing about 400 tons of pig iron in the 18th century, 1778. That with having 128 hectares of wood. Why wood? Just for the oven. Remember, you need an oven to make the metal, right? And so you need wood. Either you burn the wood or you make it charcoal and then you burn the charcoal. And so if you want, the Eiffel Tower is about 7,000 tons of iron. So if you want to build the Eiffel Tower in the 18th century, that you need 20 times the annual production of the Forge de Buffon. Or you need 20 Forge de Buffon for a year. So it's very difficult to do, in fact. Why do you do it in the 19th century? Because you have a mine coal. And what's the difference between charcoal and mine coal, in fact? So you know how to make charcoal. You take wood, you bury it, you set in fire, and then it burns a little, but not till the end. Then you stop the fire and you have charcoal. So if you look at the energy density, you have about 30 megajoules per kilogram. Then you say, well, is it less good than the charcoal, than the mine coal? But in fact, if you look at the energy density of mine coal, it's about the same, 30 megajoules per kilogram. Okay? So the energy density between charcoal and mine coal is not different, it's similar. So what's the difference? Well, here, how do you get more coal? You send a guy with a computer in his hand, a big machine, and it's eating the planet, the mine, and it's bringing tons of coal out of the mine. There, what do? You wait. You wait that the forest grows. So there you need enough surface to grow trees. Some of those trees are used to make charcoal, and then you use the charcoal. That's why in 2022, 40 million tons, still important, were produced in a year. And in 2023, it's 8 billion tons. So one solution would be, okay, I want 8 billion tons of charcoal instead of mine coal to avoid or to mitigate the greenhouse gases, if that's possible. Then you realize that you need a surface of forest that is huge. It's not available. Why we don't do the Eiffel Tower in the 18th century, besides lacking the technique and so on, the scientific knowledge, we don't have enough forest to do that. Or you can just do one like the Sainte-Chapelle was done Also, it's a crazy building if you visit it in Paris, and you imagine that was done in the Middle Age. But you can afford one if you're the King of France. You can afford one, but not more. But today we can build an Eiffel Tower every day if we want. Okay. So what is the issue between adding the fossil fuels? You may say, oh, it's piling energy sources, and so it's increasing the total quantity of energy available for human societies. That's true. But what is very different from that and that is the sun you can switch on and off when you want. So now, with fossil fuels, I can switch on the sun, which is this one. But when you are waiting for charcoal, you cannot switch on and off the sun, in fact. Why can you switch on and off the sun? It's because it's the photosynthesis of a few 100 million years ago. Okay. And so 77% of the fossil fuels, in fact, are unlimited power. The only limitation of the power is the rate at which you can inject fossil fuels in a machine. Again, a technical issue, and that technical issue has been solved. And so you have machines that are using megawatts or gigawatts. For instance, a steel industry is working 24 hours per day, and it's a gigawatt industry. Why? Because it depends on the rate at which, in the oven, the big oven, you're injecting oil or coal or whatever. And that problem solved. Okay? So so if you look at what can be done equivalent as the maximal power of the sun or above the sun, only the fossil fuels and the nuclear energy. Everything that is renewable has to be below the sun because it depends on the sun. Okay? So the conclusion, I will conclude just there. So for 2,000 years, we've been living under the solar constraint, happily. That can be debated. And then suddenly in the 19th century, we were thinking, thanks to fossil fuels, we got rid of the solar constraint. We don't need more surface for growing forest. We need more people and machines to extract fossil fuels. And so this can be done fast, and then we have the booming of those materials. But you see, if I remove the fossil fuels, you have the issue, how are you going to produce millions or billions of tons per year of materials? What is the main power source that you have available? And the main one is the sun, and then you go back to a problem of surface and not of rate of injection of fuel in a system. Maybe that's a conclusion. I have a graph that explains all that I show you just for fun. If you want to understand, we can discuss it later. But so you have the planet, and then you have the crazy guys with fossil fuels in the middle, and the end of that is
Thank you. That was amazing, amazing presentation. I'm Tiago, I'm from Brazil. And what I wanted to ask is, okay, we ended up like on a lower note here, but you were talking about it's a space problem, about the surface of the Earth so we can get this energy from the sun. But I also see, at least in my mind, that it's a problem of the material that we are using. So in your vision, like, is there any other possibility that we can use another technology or other means of capturing this energy that are seen that could be societally good as well, not only just extracting as well too much, but you know. And sorry for the long and not structured answer. We have lectures since 8:30 in the morning today.
So there are two answers to that. We've been doing that. I was stupid to go back, but I go back the other way around. So most of the time, human societies, and great ones, have been under the solar constraint. Okay, with less knowledge, less medicine, and so on. We can discuss if it was nice or not, but still. And then suddenly, in the 19th century, it changes. So the solution is in front of our eyes. The solution is to go back to be in phase with the ecosystem, and the main sources are going to be either bioproducts or low power solutions, because the metabolism of the living systems is low power. Our average power is 100 watts. Remember, the sun is 1,000. Us is 100. Okay. When you have, I have this graph that I can show you what's the difference. Let me just find it if I can use my computer at this time. So that's comparing AI with human beings. So it's an old stuff from AlphaGo, the beginning of the revolution, the AI revolution, the next step. And you have Lee Sedol. Lee Sedol is a human. He has a brain that works with 20 watts. It's 20%. And then if you look at to switch on that machine that defeated Lee Sedol, you need 150,000 watts. So the order of magnitude is completely different. So this guy is made out of water and strange thing floating in water, which is carbon chemistry. Okay? And that one is made of plastic and metals. So, and this guy is capable of reproducing, I guess. That guy is not capable of reproducing. Okay? What's the difference between a tree and a solar panel? Because they are both doing the same thing. So the tree is converting solar energy into chemical energy, and the solar panel is converting solar energy into electricity. Well, the difference is if you cut a tree and you throw it in the forest, you get new trees. Nothing happened. It's on the contrary, it's participating of the carbon cycle. But if you take a photovoltaic panel and you throw it in the forest, you get pollution, not new solar panel. So at the end of the day, the issue is the kind of industrial metabolism we are using. So instead of continuing to use that metabolism as long as we can, what we are doing now, is we go back to something similar to the living system metabolism to which we belong as humans, in fact.
But is it go back or expanding into, for example, different technologies that we can use?
Yeah, yes. It's not going back in the sense going back in time. It's reconnecting to this type of metabolism that is still in use. It's the agriculture, by the way. But the agriculture has also been zombified, but that's another discussion. So in fact, the fossil fuels are a blessing and a curse. A blessing because it allows human societies to pretend to be free from the solar constraint and the surface and the biosource products, because you know biosource is a flux, and you cannot get more than the flux. Like you cannot get more sun than the sun is producing, right? And you can also deplete a biosource. That's a species extinction. If you catch all the fish in the ocean, that's it. No more fish for the next billion years, right? But still, so the curse is that it is destabilizing the global metabolism of the planet, and it cannot last. It's not sustainable. The only thing we can do with that metabolism is slow down. Okay, slow down. Why? Because if we slow down, we are winning time to invent the next step, which is inventing this new metabolism. That's the three that will conclude on that. If there are other questions, you can raise your hand. So it silenced me. You see, in fact, that's what I teach to engineers and physicists. So the first mission, you have 3 missions. The first one is to adapt to the shocks, because we have to adapt to the ecological shocks. We have to decide to close. That's very difficult to engineers. You have to learn not to do. Don't do it. And then we have to get out of the prison of the present, which is that's one of it's a path dependency issue. all the technology you are using are path dependency, so it's very difficult to get out. With existing technologies, so I'm not advocating against anything, by the way, but solar panels may be interesting to avoid the greenhouse gases emissions. So with existing technologies, we have to save time for mission 3, and mission 3 is an intense research project. It's reinvent a metabolism that is in phase with the biogeochemical cycles of the planet. That will take time, of course. And to get that time, we have to buy time, so reduce. I haven't had the time to talk about the rebound effect, but digital technologies have a huge rebound effect. So being more efficient is not good enough because you have a rebound effect. You have to invent sufficiency. Not being more efficient in terms of energy or materials, but stopping consuming more materials and energy, which is not the same. And by the way, that's why you have computers and smartphones. It's because it's extremely efficient. Before, humans were in the computer, because it was a room. Now you have the computer in your pocket. That's because it's extremely efficient in terms of materials and energy. And what do you get? A huge rebound effect of consumption of materials and energy in the digital technologies.
We will collect a few questions. I come back.
Thanks. You were mentioning, sorry, I'm Jonas from Switzerland. You were mentioning quite early on in your presentation that like the economists are not talking with the engineers and so on. That's quite a huge problem. And you kind of also trace back as far I can recall that, like, for example, like we still don't know how to recycle a lot of products and so on. And but I think like it's kind of interesting also to look at the history of like the idea of recycling, because I mean, like it was invented more or less, as far as I can recall, like in 1960s, 70s, for the petrochemical industry to continue selling their products and so on, saying we're actually part of the solution. Don't worry, guys. Like, yes, okay, our product might be polluting, but we can recycle it. Like, we are actually part of the whatever cycle and so on. This can go on, and then this has kind of been repeated with CO2 emissions, where also I've said this already last week, but yeah, where economists have come up first with the idea, okay, we can kind of recycle emissions, like by pulling them out of the air before this even existed. And like now, 50 years later, we still don't have the technology for recycling for most of those things. So my question is kind of like, how like shouldn't we kind of turn it around and like say, okay, we can not use a technology, or in general, like a technology shouldn't be used as long as we don't have, as long as we don't know to recycle it, instead of the other way around. But I also understand obviously that there's an industry interest to do, like to use it and say, yes, we will recycle it at some point in the future.
I'm Theo from Germany. How realistic do you think are the transition plans to a green economy, if something like this can ever exist, basically? Because you mentioned the fact that only for the solar voltaic panels, you need half of the copper that is produced worldwide in a few years. So is it even possible to have that kind of transition realistically, materially speaking?
So I totally agree with you. I'm answering to you. I totally agree with you. It's even worse than what you think. For instance, I have colleagues in physical chemistry that are inventing recycling physical chemistry, right? For instance, they take electronic waste and then they want to take out the rare earth out of the soup to use it. But what the funny thing is that suppose you invent a recycling, they are very clever and very precise. They have high-tech recycling techniques. But then somebody in China decide to change the formula of the magnet. For whatever reason, economical, technological, or whatever, then you're not sure your recycling method doesn't work. In fact, the people producing stuff don't care about the people inventing the recycling. There's no link. They don't talk to each other. It's a different industry. That's one of the big issues. And in fact, if I was president of the world, I would say you're not allowed to invent and sell a product if it's not recyclable, and then we have to discuss what does recycling mean, okay? Because in fact the circularity it's an obvious answer, because we have living beings on the planet for the last 3.8, 3.9, even 4 billion years. Why? Because there are those cycles, the carbon cycle, the water cycle, the nitrogen cycle, and so on. So those cycles exist, and that's why I'm here talking to you a few billion years after the beginning of okay. What's the difference? The difference from a metabolic point of view, an industrial metabolic point of view, you've understood that I see metabolism everywhere, is that living beings use the geophysics of the planet, as I explained with volcanoes. So the geophysics of the planet is used for the recycling, the geochemical cycles of carbon, water, and so on. Okay, the industry we want to switch on is not using the physics of the planet, the geophysics of the planet. It's using the brains of people, of engineers and physical chemists and all those guys inventing a physical chemistry in the lab, not taking into account the planet. So again, we have the solution in front of our eyes. In fact, when we use biosource materials, it's not necessarily sustainable because it's biosource, by the way, but it can be connected to the biochemical cycles. So what is the very good smartphone sustainable? It's a smartphone when it's broken or it's the end of life, you eat it. That's it, it's recycled. Not you personally, but you can compost it, okay? You can ask something else to eat it, mushroom, whatever you want. But that's a way to, that's how it works. And those solutions exist, and humans have been using those solutions for longer than we are using fossil fuels. So that's the invention of the metabolism. So no, the answer, is it realistic? No! No, because in fact, why it's not realistic? Because it's an engineering point of view. I will show you this one. In fact, the technological system is zombified. That's my main message. And then people think, oh, okay, some technologies are zombified because they're not sustainable in terms of materials, energy, whatever. Okay, if I invent green one, it's going to make it. No, because that's not how technology works. It's not because you invent something that it's interesting. In fact, technology works if you change the political system, if you change the socio-economical system. Like I was saying in the introduction, I'm not discussing degrowth in economical terms because I'm not an economist. I don't want to enter that debate. But there will be a stop of the growth of using materials. That's physics. I'm pretty sure of that. It's pretty obvious, okay? Then do whatever you want from an economical point of view with that, but that means the economical model has to change. The socio-economical model has to change. The steady state economy, 1977, Herman Daly, it's also formulated. That means you have to invent some form of socio-economical system that is at steady state. What people don't want to stop is the growth. They think I change there, I change the red square there, and I keep the same socio-economical system. I don't think it's realistic. We can discuss about, think about that. Well, you better think about that because you will live in longer than me. But you may discuss about that, but I don't think it's realistic.
But let's say we wouldn't grow from this point on. Would it be possible?
Yeah, why not? There is a kind, I don't have the time, but if you look at the Holocene, there is a kind of stabilization of the planet. And the climate was stable, more or less, and there was still a fluctuation, but it was more stable. The amount of estimated biomass, plants, and so on, some kind of stability. And in fact, the emission of greenhouse gases and the rest of all the ecological disasters are changing that stability, and the Earth is moving to another different path. So when you look at the beginning of the Holocene, it's the same beginning as the Neolithic. So there is a hypothesis that it's because the climate was stable, because the ecosystem were rich and stable, that human societies could thrive on, invent empires and civilization and so on. And what we are at the end of that, because we are perturbing that cycle, and we have to go back to some kind of stability. We have some scientific knowledge about that. People above there, the scientists there, know about that. But still, below it, there have been propositions, Herman Daly, about the steady state, the degrowth movement. So they try to reinvent economical models, socio-economical models compatible with a steady state use of energy and materials. So you don't have to be pessimistic because it has existed before. But the challenge is still worrying. Yes, that's you.
Yes, hi. My name is Leo from Germany. Thank you very much for the presentation. I have a little bit more of a technical question because I've done some similar like modeling on copper limits in the last semester as well. And like one thing which I was stumbling across a lot when like trying to get much of like a certain raw materials left is that the like the undiscovered reserve stock is like something which is very hard to estimate and like which is like a very big like dark number which you can't really observe. And luckily for copper at least we found that there's like at least some studies estimating it like based on geological data, but I know that for other materials which also like where the percentage of it which is like gained from host metals and not just taken out of the ground is like way bigger, that it's like way harder to estimate. And for example for lithium I think we didn't really find much of estimate. I'm not sure, maybe like I'm wondering how you tackle that in the work which you did, and yeah, in general what you could say to a scientist interested in that.
It's kind of related because also to what you were mentioning, when you mentioned also the graphs, you put the estimates, and one thing is the resources, but they are not easily recoverable. So even if there are deposits, and even if geologically there is copper, most of that is not recoverable because they are very highly dispersed. And it's for me it's interesting the case of rare earths, for example, which are, I think you were mentioning, and that's highly interesting how that is even much more complicated than the case of copper. And it's not about recycling, but the fact that in itself they don't they are that available, and yeah, it's basically building on Leo's question.
So there are two types of answer to that question. The first one is focusing on geological issues, scarcity and stuff like that. Of course there are uncertainty. Well, nobody knows exactly how much copper you can use or you can mine. But what we can do, what I've shown you is to, with the existing data, what can I say? Okay? And then I don't find 3,000, I find 2,080. Okay, then it's worrying. Okay, so it's a usual political trick to use the uncertainty for not to act. And there are still papers saying, okay, but one thing for not acting is looking before 2050. So you don't see that. And then you say everybody that is looking beyond 2050, it's nonsense because it's unpredictable, which is true. But now, if you want to work those questions seriously, say with existing data, what can I say? Now, if you hope to find a huge copper mine or rare earth mine hidden in Greenland, after it's been annexed by the United States, then suddenly we find a huge copper mine or rare earth mine, whatever you want there, or somewhere else in the planet, you have to think about system. It's not copper or fossil fuels, it's copper plus fossil fuels. So if you want to mine, suppose you find much more copper, if you want to mine it, where do you find the power? For the moment, in the fossil fuels. It's the same with space mining. So it's again the frontier. It's an American way of thinking. So it's we've reached the frontier, a first frontier, which is the planet one, planet boundaries, right? So let's go further away. Let's go mine space. Why not? Why not? It's technically, I cannot say it's technically impossible, but then you look at the physics of the problem. Besides going to asteroids and catching them, but bringing them back to Earth, landing, and how much power do you need to do that? Theoretically, right? Not just imagining it's possible. And then you see that doesn't fit where do you find that power? Doesn't fit the thing. But then you can think of other type of societies. You can start playing with anthropology. Suppose now you have a low power source, but you can still mine copper or aggregate copper. And then every 100 years there is the global world copper feast where we have enough power to mine copper. See? And then, but it's been like that, and you know, the forestry is a bit like that. You know, there is a way to handle a forest. If you cut all the trees in 1 year, then you're doomed. So we've learned to deal with that kind of flux. We will learn to deal. So there are two answers. Okay, playing with the uncertainty for not acting, it's not a good idea because the issue is still there, and I didn't tell you the real issue behind there, but that will be another time. And second, where do you find the power to do that? Okay, even if you find a huge copper on whatever planet of the system, a source, how do you get it back? Then you fall back to fossil fuels or not fossil fuels. Do you have enough fossil fuels to mine copper for the next millennia? I don't think so. And so I answer both questions, I think. But what is interesting about rare earth that you have to understand is that in fact it's not a geological problem per se. Of course, there is a finite amount of resources on the planet. Of course, there is dilution and so on. But what is interesting is that the way we build our technology is creating the depletion. That's an important thing I am explaining to engineers, physicists, and chemists. The way you invent materials, you are creating the depletion. It's built in, like a nerd say. It's not a bug. It's a feature. Okay, which means that the metabolism, the industrial metabolism behind it, is not correct. But we can still invent another one. I hope.